at things. I can remember when I was probably some of these gentlemen's ages that my father sent me out to Nebraska to visit a cousin out there. And we were busy making these little haystacks that looked like loaves of bread. We made a lot of those, and it was really interesting. I was a young man driving this new equipment and everything that this farmer had out there. And he let us work at that for about a week. Sent us into town. He said, "Now, boys, why don't you go into town and check out the town, but be sure you check with that old Indian in there and see how bad a winter it's going to be." So we went in there, and of course we had to check out the movies and the girls and a few other things there. And finally found this old gentleman. And we asked him, "Sir, his father wants to know how bad the winter's going to be." And he says, "It's going to be bad, heap much snow." So we went back and told his father that, and he said, "Well, you boys get out there and you keep making those haystacks." So we kept making those haystacks. Another week went by. He sent us back into town. He says, "You ask that old Indian how he knows that winter's going to be so bad." So we went back in. Of course, we had to bowl a few lines and a few other things there, too. But we finally found him again. And we said, "Now, his dad wants to know how you know all of this, sir." And the old Indian looked right at us and he says, "Easy. White man make many haystacks." Well, I'm very happy tonight to present Mr. John Felt. He's Station Chief of the Johnston National Weather Service Forecasting Office. And he's got some new things that are going on up there, and he's got a program that he's been on the road with, and I understand he's been on the road at 9 o'clock this morning, so we're really stretching his day to the limits here. So I think you'll enjoy it, and with that, I give you Mr. John Felt.
Well, good evening. I need to get situated here first of all because I need 3 hands. I've got the microphone, the pointer, and the slides here, but I think we'll get situated. You know, this is exciting for me because this is my first spotter training of the season. Ever since the floods last year, all I've done has been giving talks on the floods, and it's very nice for me to get out and start talking about spring weather because that's still what I get excited about. That's why I became a meteorologist, because of all the thunderstorms, and this is what gets me all worked up for the severe weather season, which is right around the corner. Usually about the time I start doing these, we start have thunderstorms within the next 2 or 3 weeks. So I've got a lot to show you tonight. There's a lot of new stuff going on. I don't give as many of these talks as I used to. I think Joe Sullivan was here last year. Anybody remember Joe Sullivan? Was anybody here last year? A couple of folks. Joe's moving. He's moving to Cheyenne, Wyoming in about 3 or 4 weeks. And Jeff Johnson is taking Joe's spot, so he might be down here next year. But like I said, there's a lot of stuff going on in the world of storm spotting, and I want to show you some of the things tonight. I've got a lot of stuff to show you. What I did is I actually combined one of our meteorologists shows the slides and another one shows the video, and I sort of liked them both, so we're going to show a little bit of both of them here. And once again, the thing is to have you know when you walk out of here of what's going on with severe weather. And let me tell you, it's not easy. Before I was up here in Iowa, I was in Kansas, and you see the big tornadoes in Kansas. Those are easy. You can spot Kansas tornadoes from a long way away, that you know what you're looking at. Here in Iowa, they're very difficult to spot. The interesting thing that I learned was that there are more tornadoes here in Iowa per given area than there are in Kansas. We get a lot of weather here. I never like to tell this to the Chamber of Commerce, but actually if you look at the number of the type of winter storms, if you look at the type of summer weather, tornadoes, severe thunderstorms, and there's a meteorological reasoning for all this. This is the action spot in the country here in Iowa, I'm convinced. And I didn't even mention floods before last year. Now we add the floods, and let me tell you, there's no more active spot than Iowa. When I was down in Kansas, usually June 15th, the jet stream goes up to the north, and it's real quiet after about that time. Usually about June 1st. So when I was down there, I wanted to come up to a place where the weather would be active, and I never thought it'd be this active as here. After the last 2 years, I'm not sure about it anymore. But, well, let's start off here. If we can get the lights, and I'm going to get situated because I tend to wander around here a bit. Okay, can we get the light on maybe it's the first slide here? I think we need the light on. There we go. Let's see if I can reverse it here. Aha. Okay, what we're going to talk about is actually from the Advanced Severe Storm Spotter Training Guide. And I'm going to start out telling you what causes severe thunderstorms. Now, we've learned a whole lot over the past couple years on tornadoes. And as you'll see in a little bit, about a half hour or so, I'm going to show you what our new radar's indicating. And that's going to tell us a whole lot starting this spring. But basically, there are 4 elements that we look at for the development of severe weather. First of all, the air has to be unstable. Basically, if you have stable air, you're not going to get the cumulus clouds to rise. You're going to have them probably not even form, but if they form, they won't do much. So one of the clues when you're looking out there on a warm summer day or spring day is look at those clouds. If they start to, turn it, the cumulus clouds, the puffy clouds, if they just don't go too far, if they get a little bit up in vertical extent and sort of stop, you know that you don't have enough instability most likely. Now, there's another reason. It could be that the winds are so strong they're keeping them from developing the extent. But that's one of the clues that you need. The other thing you need is moisture. If you don't have moisture in the air, you're not going to get the clouds to start with. And a lot of times you can have the instability, but not the moisture, but you need both. The third thing you need is something to lift the moisture. A lot of days in Iowa, it's very typical, real muggy air, maybe the dew point's around 70 or 72, a lot of moisture in the air. But if you don't have something to lift that moisture, you're not going to form clouds. And there are many, many days we have the moisture around, but we don't have clouds. It's just a muggy day. So you need something to lift it. And that's one of the reasons why down in Kansas and Missouri, you don't get many severe thunderstorms in the middle of summer, is because you don't have the lift. The fronts don't get down there. And finally, another way we can get the thunderstorms is low-level convergence, winds that are converging together. And if they converge at the Earth's surface, sort of coming together, they can't go down. The Earth is there. They have to go up. So they start to go up, and that's another way you can get your clouds and then your thunderstorms. Okay, this talks a little bit about stable versus unstable. It just basically says an object is stable if, when moved a small distance from its original position, it returns to that position. So if you have a parcel of air that's beginning to go up, it'll tend to come back to where it started. If it's unstable, if you move it a small distance, say a front pushes it or lifts it or that convergence, it accelerates away. And that's why you get those cumulus clouds billowing up to 50 to 60,000 feet, because the atmosphere is unstable. So if you're out there on a day, once again, if you know it's real muggy, you know the moisture's there, you might not know if the lift is there, but if you start seeing the cumulus clouds rapidly accelerating vertically, you know you have that instability. This just gives you another idea what it'll do for unstable versus stable or neutral air. Something we can look at just to give you an idea. If it's unstable, say this is the environmental air, or what the temperature of the air is up there, and this is the causing the lift, it'll continue to rise. One of the other things that's very critical to what you would get, whether you get just plain old thunderstorms with no severe weather, all the way up to tornadoes, is what the vertical winds look like. And this diagram here, starting at, this is the Earth's surface here, and it goes all the way up to 30,000 feet. Now convection, I'll be talking about convection. Convection is just the lifting of the air vertically into thunderstorms. Okay? So basically, if it's unorganized convection, and what I mean by that is your typical day when you get a lot of clouds, cumulus clouds building, but they're really not doing much. A lot of days are like that in the middle of summer. That's unorganized convection, and the winds are very light. There's not much to it, and that's typical usually in the mid to late summer. Once again, especially south, definitely south of here, but often in Iowa as well. Very light wind profile all the way from the Earth's surface up to about 30,000 feet. On the other hand, one of the things that we look at, and our Weather Service meteorologists in Kansas City that issue tornado watches, is this is one of the key ingredients, is the winds. Once again, this is just showing very strong winds. The little filled-in triangle is worth 50 knots of wind, and these are worth 10. So this would be 70 here. This would be 90. And the stronger the winds, the better sign that you're going to have severe weather. Now, how can you tell that? Well, it's not real easy to tell, but one of the things that you can do is look at the upper level clouds like cirrus clouds and see if they're moving very fast. That's one clue that the winds are strong. But other than that, it's sort of hard to determine. The other thing what I'm going to point out in a little bit is the way the winds turn. If the winds are turning like that, this is at the Earth's surface, a southeast wind, and then going from the southwest aloft, that's another key ingredient in tornado development. You have to have that turning of the wind for tornado development. Let's say you just had real strong winds, but they all came from the same direction. You probably wouldn't get tornadoes. You could get severe thunderstorms, but you probably wouldn't get the tornadoes. Now, there are many different types of thunderstorms. It's like everything in life, I guess, nothing's simple. You just can't have a thunderstorm. You have many different types of thunderstorms. First of all, you have a single-cell thunderstorm. Those are the most common type of thunderstorms we have. Then we have multi-cell cluster-type thunderstorms, multi-cell line, and then finally supercell. This is the least common. This is the one you normally see down in Oklahoma and Kansas. Big tornadoes come out of them. This one's fairly common here, and this one's also fairly common as well. Single cell is non-severe or severe. All these can be non-severe or severe. And then finally, if you do have a supercell, it's always severe. Okay, this is another graph that indicates sort of what I was telling you about before. A little bit more complicated than the other one, but actually it's a pretty good graph. The two ingredients that I told you for severe weather are shear, and that's the turning of the wind. So the vertical winds, and then up here, the updraft strength, and that's a sign of instability. So remember, when we're talking severe weather, we're talking about instability and the turning of the winds. Those are the two big ingredients that we're looking at. Now, you get all sorts of different type of thunderstorms, but it's sort of common sense. Let's go through this here. Ordinary thunderstorms. Okay, well, if you have weak updraft, it's low on the graph here, and no matter how much shear, if you don't have much updraft, you're going to have pretty much a typical thunderstorm. Then you start getting more updraft, stronger updraft. The thunderstorm's rising very rapidly. You can get some squall lines, which we'll talk about in a bit, and some multi-cell. And then finally, let's say you have a whole lot of updraft. It's just really, the updraft is very strong, but you don't have much shear. What you'll get then is you might get what we call pulse storms or slow-moving storms that will give you flash flooding. And then way over here, on the top of both scales, a lot of updraft, a lot of shear, that's where your supercells. Basically, it's saying that everything's in place to get supercells. Okay, I'm going to start off talking about single-cell storms, give you a couple examples. Once again, this is the most likely type of thunderstorm that we get here in Iowa. If we do get severe weather, it's brief and it's isolated. These are the ones that usually, if we issue a warning, it's after the fact, mainly because someone here will call, they'll say, we've had 3/4 inch hail. And by the time we get the warning out, that's probably all the hail you're going to get. It's not going to be much to it. It'll just be usually a one-time event. You might get a brief gust of wind to 70 miles an hour or something like that. But the main thing is it's very, very spotty. And it can happen anywhere within that storm. As I mentioned, very hard to predict for that type of storm. But on the other hand, the danger is fairly low too. It doesn't do a whole lot of damage. And most of the time, it's not even severe. This is an idea of what the ordinary thunderstorm would look like. This is an updraft of air, the cumulus cloud. And this is time, so it goes up to 20 minutes. Sort of see as the updraft develops, gets higher up here. This is in thousands of feet. Eventually, it gets to a certain part, and then you start getting downdrafts. The rain sort of falls through the downdraft, and eventually it just dissipates. So it doesn't last real long. You usually don't get a whole lot with it. This is heavy rain. You get a period of heavy rain, and that's your typical thunderstorm. Now, what we would call the pulse severe thunderstorm is a little bit different. What it would do is it lasts a little bit longer to start with, and sometimes what you do is when you get towards 20 minutes or so, when this downdraft is coming down, you can have a pulse of severe weather. And once again, it's very brief. It's usually maybe some hail, maybe winds to about 70 miles an hour, but it's just a pulse as the thunderstorm is actually falling apart, and then it's gone. It's really very hard to predict for that type. This is a picture of a thunderstorm, and it sort of gives you an idea on radar what it might look like, but you can sort of see this is the updraft right here. This is the updraft. And it's a single cell, and what we mean by cell is the updraft here. There's usually just one in here, or there would always be just one in a single cell. And up here, we start getting in the anvil. The winds are stronger, so the real strong winds are blowing the anvil. What can you tell if you were out there and saw this right here? Well, one of the things that you could tell is certainly you have a pretty good updraft to cause all that upward motion to bring that cell as high as it is in the atmosphere. You also know to get that much moisture to form that thunderstorm that you do have moisture in place. You probably know that the winds are fairly strong because they're sort of blowing this anvil off here, so the winds are pretty strong. But you don't know much about shear. You could look at it and sort of see maybe if it's rotating, but you really don't know if you have the shear. In this case, you don't have much shear, and basically it's just probably an ordinary thunderstorm. And once again, you could get some brief severe weather with it. Here's another picture, same thing. Here's your updraft. Then this is your cirrus anvil, higher level winds. The next type of thunderstorm is a multi-cell cluster storm, and this is very common. Severe weather can occur with these storms. We can get downbursts, moderate-sized hail, flash floods, and very weak tornadoes. A downburst is basically as the thunderstorm sends some of the mid-level air, it sort of diverts it down. So the winds are usually stronger aloft. What they're doing is they're being temporarily diverted down to the Earth's surface, and you're getting very strong winds. Once again, it can go in a multicellular storm, it can go 80, 90 miles an hour or even more. So you can get very strong downbursts of wind. And the severe events most frequently occur near the updraft-downdraft interface, and we'll show that in just a minute, and usually in the southwest part of that storm. And that's an area, as storm spotters, you're going to want to look at. Once again, there's a moderate degree to predict these type of storms, and there's about a moderate degree of danger to the public. But these are definitely ones that we want to know about. This gives you an idea of what you'd expect. Once again, the two things we're looking at here are updraft strength and the shear, or the turning of the winds, two very important ingredients. Now, we're assuming in these examples that we already have the moisture to form the thunderstorms. So what you'd have in this case, you'd sort of see that the thunderstorm, the top is not nearly as high as that. That's because it's a weak updraft. Weak, it's not pushing it way up here. Strong updraft, it's pushing it way up here. So weak updraft, but a strong downdraft. So a lot of energy coming down, what we call a microburst. We had one of these at the airport 2 years ago in Des Moines, and we had winds. We were sitting there, and we knew we had a pretty good thunderstorm, but nothing real special about it. And we had winds of 80 miles an hour. And I remember driving home, and you could hardly find any damage. It was just real localized. It knocked over a dumpster, but that was about it. Very, very small. On the other hand, what we have here is we have a very strong updraft. Well, how can you tell it's a strong updraft? Well, for one thing, you can tell because if you look out there, it's very high up in the atmosphere. That's probably the easiest way. But the other clue is this thing up here. We call this an overshooting top, and I'll show you a lot of pictures of that. An overshooting top is just saying that the updraft is so strong that it's pushing it up past where this cirrus is forming. And that's a sign of a very strong updraft. If you have that overshooting top, if you can see that, I'd say your chances are pretty good that you've got a severe thunderstorm right there. Okay, so what would you expect? The red here is your updraft, and here's your downdraft. Now, in this case, you have the potential for flash floods, and you could get single or multi-cell severe storms. This is your hail. You can get some hail with it. Okay, this would be the multi-cell cluster storm. One of the things that when you have multi-cell, and these are the different cells, each one represents an updraft. And if you look at it, an actual picture, which we'll show in a minute, you'll actually see these different updrafts. And what they do is they just sort of work their way through. Right now, this is a primary updraft in cell 3. But then next one, as this dissipates, it'll go to cell 4 and then cell 5. And in this case, cell 1's already dissipating and falling apart. Now, if you're looking at it on, say, radar, or, in this case, just looking down at it, the greatest risk of severe weather will be in this portion of it right here, in red here. So it's not going to be way out here. That's going to be something real important. We're going to show a lot of diagrams on that, where you want to look at that. The southern part of the cell is where you want to basically look. Here's another one, a multi-cell. You can sort of see what I showed you before, cell 1, cell 2, cell 3, and cell 4. If you look at time, you see cell 1's dissipated. Cell 2, which used to be the primary one, that's beginning to dissipate. And when it dissipates, that's when the energy comes down and you can have your very high winds. Cell 3 now is becoming the primary one. And then down here, finally, after 20 minutes, 1 is totally gone. 2 is just about gone. 3 is beginning to dissipate. And once again, that's where your winds are going to be. And 4 is beginning to have the updraft to take over on 4. Here's a good picture of a multi-cell cluster. You can sort of see the different cells here. Here's 1, here's 2, here's 3. Looks like there's 4 on here. This one, I can't really tell over here, but this one's probably, I can't really tell if this might be the primary one, but one of these two are actually pretty close here to be the primary one. Probably up here, it's dissipating. With time, each one of these will go a little bit stronger. There's another picture right there of a multi-cell cluster. One of the things sort of interesting for me to do is to look out, without looking at all the weather maps and all the other gizmos we have, is to try to tell what's going on. And I don't know, maybe it's my imagination here, but it looks to me like they're leaning a little bit this way. Does it look like they're leaning to you? A little bit like this? Sort of leaning. Well, one of the things that indicates is that you have very strong winds that are pushing it this way, which can be good or bad. Actually, if they're starting to lean, that means that the updraft is not strong enough to counteract the strong winds. So the strong winds can actually cap it and cut off the chance for real strong weather or severe weather. On the other hand, it does mean that the winds are very strong, so that if your updraft can compete with that, you have a chance of getting to supercells. Another, with a picture here, shows you the different cells. This one's just about dissipated. This one has dissipated. This one here is pretty much dissipated. Cell 3. If you look down on the ground, it looks pretty dark here. That's probably where most of your rain is. Once again, this would be where the winds are coming down. This would be their best spot for severe weather, mainly winds. 4 will be the next one to go, and 5, you're just getting your first little cumulus cloud there. Another view of different cells. Sometimes they're hard to see. You have a lot of cirrus and a lot of scud clouds here. But if you look behind them, this is more what you'd see in Iowa. It's never all that simple here to spot, but you can sort of see the different towers behind it. Here's another one. One of the other secrets that if you're out there spotting, what you want to look at is if the cells themselves are real clear and crisp. These are real, sort of like cauliflower. These are real clear and crisp versus fuzzy. If they're real clear and crisp, that's a sign of a very active updraft and a better sign of severe weather. If they're more fuzzy, that's a sign of ice crystals, and that could mean that it's not quite as severe as if you see something like this, real clear and crisp. There's another example. Anybody see anything on here that we just talked about? Overshooting top, right. There's your overshooting top. Now, in meteorology, they teach you that right here is what we call the equilibrium level. And what that means is if you have a parcel of air rising, when it gets to this point right here, it'll no longer be unstable. It'll become neutrally buoyant. If it gets past this point, it'll actually be stable, so it'll come back to that point. So what it does is it actually comes up here, and then it'll sort of stop right there. But what you're seeing here is that the updraft is so strong, it's actually pushing into stable air and going beyond it. So it's indicating a very strong updraft right there. Once again, if I saw that, I'd say the chances of severe weather would be pretty good with that storm. Another multicellular storm. This one here is sort of interesting. It might be more difficult to see here. I've seen it a few times. This is a downburst or a microburst. And what you're seeing here is the way this sort of bending here, they call that a foot. You'll see it come out here. So when the wind comes down, it's coming down so strong, it's spreading it out this way. It'll also spread it out this way. And if you see signs like this is the rain, being spread out like that. That's a sign of very strong downburst winds. And these are the winds that can go up to 100 miles an hour at times. Very clear sign if you see something like this. Once again, the force of the winds are hitting the ground, pushing it out horizontally, and then actually curling it up a little bit here. That's what they call the foot of the microburst or downburst. And you can sort of see it right in here. That's, once again, a sign of very, very strong winds. The next type is a multicellular line type storm. And that's basically your squall line. We get those, and to tell you the truth, I haven't seen as many of those in recent years than I have in the past. These are the ones that are often really keep us running because we've got warnings out for all sorts of counties. And I haven't seen these quite nearly as much as I have in the past. But the severe weather you can get with the multicellular line can occur as downbursts, small to moderate sized hail, some flash flooding, usually not a lot of flash flooding because it's a line and it's moving, and then weak tornadoes. Severe events occur near the updraft-downdraft interface on the leading edge of the storm. And that's different from the other multicellular cluster. And we have a moderate degree to predict that. Now, what's very typical is if you're looking at a radar picture on TV, or if you see a line coming, this might be all the way up in Minnesota somewhere and going across Iowa and all the way down into Missouri or someplace like that. It can extend along a very long distance. But at any given time, you just have certain areas that are more likely to produce severe weather. Now, one of the tips that I always say look at if you have a TV and you're trying to get an idea is, you know how usually what our radar will show, it'll show from greens to reds. Red's usually the most severe or the most reflectivity. And now, if it's a real tight gradient, and what I mean by that, if it goes from no rain all the way up to a real bright red, but in a real short period of time, that's usually a good idea of that it's a severe storm. And I'll show you, if I can remember, I've got some other pictures I can show you what I mean by that. But the main point here is along this line, even though there's a line of thunderstorms, there's usually only a couple points that are actually producing severe weather at any given time. The other thing is what we call bow echoes. If it's bowing out, if it's pushing out ahead of that line, that's a good sign of severe weather. Another thing is if it's at the end of a line, that's a sign of severe weather. And one of the reasons is because the moisture is feeding into that, and this one has to compete with this, but there's nothing else down there. So this one we want to look at. Okay, this gives you some pictures of lines. Here you have a line of thunderstorms moving towards you. You really don't have any idea what you're going to get with that. There aren't a whole lot of clues other than you have a line. You really can't look at it and say, well, this part here is going to be severe and this isn't. You can't say that at this point. The first thing you'll get is you can get a leading edge here of a roll cloud. And this is one where we always get reports of tornadoes all the time. Oh, we got a big tornado on the ground or whatever. It looks real dark back behind it. And the reason it looks so dark is because that's where your rain is. Now, if you were standing right here, the first thing that you'd feel is a wind at your back. And what that would do is that's the wind that's feeding up into here. Actually, that's what's causing this. And what you're doing, that's the wind that's feeding up into this. Next thing you do is as this approaches, you'd feel the gust front. And you'd feel the very cold or cool, strong winds that are coming down from mid-levels, coming down and sort of hitting you along right before the rain. Next thing you'll get the rain. The rain is being pulled down by that downdraft. So that's what you would expect. Now, where would the severe weather be? In this case, it'd be caused by those mid-level winds coming down, and that's where you get your high winds, right along the leading edge. Now, if you're new to storm spotting, the secret is on these lines here, it's going to be at the leading edge most times, but your other type of thunderstorms, it's actually going to be in the back part of the thunderstorm. So you don't want to be confused. If you're spotting, and you have to know if you have a line here. If you have a line, it's more likely to be at the leading edge. But if you have a cluster-type multicell or a supercell, it's going to be in the back part of the storm. So you don't want to say, well, I didn't get anything, it's rained, it's over. That's actually when you're getting to the point that you want to be most cautious and be looking for the tornado. We'll talk a lot about that. These are some more pictures of lines, multicellular line storms. They can look real impressive. Probably the most impressive storms are the line-type storms because you have a lot of low clouds. The low clouds are caused by the rain-cooled air from mid-levels, cool air, rain, a lot of moisture forming clouds at low levels. These clouds are very, very turbulent. They'll be turning and a lot of this. They're probably the worst looking storms. I mean, even myself, I'll see a good line come in and I'll be thinking, boy, we've got to get severe weather with us. And a lot of times you don't. You just get some gusty winds, 30 to 40 miles an hour, and a lot of heavy rain. Maybe some small hail. It's not uncommon to get small pea-sized hail with this. This is what it'll look like. It'll look real bad as it comes in, rolls in. Here's the leading edge. That's that rain-cooled clouds in front of it. It could be a shelf cloud. Then this is your rain. Some more pictures here as the shelf cloud passes over you. Okay, now we're getting into, let's go one more here. Give you an idea of some of the rain behind it. Like I said, it looks pretty bad. Okay, the next one we want to talk about is supercell storms. Supercell storms are more common in Kansas and Oklahoma in the plains. We do get them here. They're usually more difficult to spot a tornado because of the rain. Down in the plains, they're a little bit easier to spot. But we do get them here. We usually get them on days in the early spring, although they can be any time, but usually your big severe weather days is when you'll get supercells. And that's when we get our tornado outbreaks. One of the things that I learned not too long ago, and I don't know if Joe mentioned this last year or not, whoever was here, but what makes a supercell? Well, a supercell, by definition, means it has a rotating updraft. It's not a supercell if it doesn't have a rotating updraft, and hopefully we'll have some time to show you why that's important to the radar that we now have in Des Moines. I have a couple examples of that. So remember, if you have a rotating updraft, it's a supercell. This might be, looking down at it, this might be what you would look at. Here's your thunderstorm. What you'd have here, let's say you're standing here and the storm is moving towards you. The first thing that you'd be likely to see is some light rain, maybe some gusty winds. This is a front here with the winds coming down, but nothing real strong. Then you'd get into your heavy rain, your hail, and actually you're going to be looking down towards the back part of the storm for that tornado. That's where you're going to want to look. Now, if you're up here spotting and this thing's coming towards you or here, you're not going to see that too good because all this rain's going to be in your way. The best place to look at it is actually back here. It's actually, this is the rain-free base is what we call here. And it's actually a very good place to look at it. So you want to get behind it, maybe to the west of it, if it's moving east, or maybe the south of the storm. But you don't want to be up here to the northeast or the north. If you're up here, you're not going to be able to see it at all. But this is where your updraft region is. And this is your what we call the flanking line. It's the towering cells that will feed into that. I know I'm hitting you with a lot here, so if you're don't feel like you have to get everything here, but hitting you with quite a bit at one time. Okay, this is a supercell, another way we can look at it. Once again, let's say you're standing right here, and this is where you're going to be looking for your tornado. You're not going to see much because you're going to have all this rain here. Likewise, if you're on the other side. What you want to do is get behind it or to the west, and then you'll get a good viewing angle. But what would you see? Well, we've talked about the overshooting top. We've talked about a little bit about the cirrus anvil that spreads out. A lot of precipitation here. The hail would be in here. And now, this is a lowering of the base here. This is what we call a wall cloud. This is a very good sign of the possible development of a tornado. Now, it's interesting, once again, if you haven't been in spotter classes before, there's little or no precipitation back here. So if you're standing here and the storm's moving towards you, you might think the worst is over. You know, the rain's over, you got all the racket with the hail. Hey, it's over. But this is where the tornado's likely to form. Now, one of the things that you might have heard is, well, the sky turned green. You know, we hear that a lot. Well, one of the things right before the tornado, one of the things, the way you'd explain that is that with all the light getting in here, going through that hail, refracting through the hail, it's causing some coloring, perhaps green, and that's why it looks green right before the tornado. That's real common as it goes through the ice of the hail, the visible light. But this is the area you'd want to look. You'd want to look at this lowering of the rain-free area back here, and that lowering would be called the wall cloud. Here's just a picture of a thunderstorm, a supercell. Once again, you don't see rather than several cells, you basically see one updraft, one main updraft here. You might see some smaller ones here that'll feed into the flanking line, but you have one main updraft here. Can't really tell if you have an overshooting top. You might have a little bit there. Here's another picture. Here's some of your cirrus here, so you definitely have an overshooting top here. Very crisp. Once again, if it's real crisp and clear like that, that's a good sign of an active updraft. Here's your cirrus, your overshooting top. Very strong thunderstorm. You probably can't tell just by looking at it that it's a supercell, but certainly you know you have a possibility of severe weather in there. Another view, looks like maybe a little mammatus clouds here. That's on the underside of the cirrus. And I'm not sure if we have any other pictures of them here, but it's sort of a low-hanging type cloud under the cirrus, and that does not lead to severe weather. There we go. And that's quite common. You see that quite a bit. I remember when I first started doing spotter classes, it was thought that there was a correlation between the mammatus clouds and severe weather. And about all you can say is it means that you have a strong thunderstorm. So in that context, maybe you do have a chance of severe weather. But there are a lot of thunderstorms that have mammatus that don't produce severe weather. Another picture of a supercell. Okay, let's talk about the wall cloud and how it pertains to the development of tornadoes. Well, this is very important, for you to understand and also for our forecasters to understand, because we are going to be using our Doppler radar, and the same things that we're teaching today are things that we need to do. We need to know. But if you get a wall cloud, one of the first things that you want to do is see that it persists. It's usually not the minute you get a wall cloud, which we have back here, that you're going to have your tornado immediately after that. It's going to last for a while. So we do have the luxury of watching it for a little bit to see what it does. The other thing, what you want to do is there are a lot of wall clouds, but not all of them rotate. You want to see if it has rotation and that it's persistent. So first of all, if you have a wall cloud, we'd like to know about it, but I'd also be pretty concerned that at least you have a severe thunderstorm. If that wall cloud is rotating and it's persistently rotating, that's one more clue that it's getting close to forming a tornado. Surface-based inflow. Well, how would you determine that? Well, what you do is you'd see small particles of clouds being fed into that. That's another sign. And then rapid vertical motion. Typically what you'd see is you see maybe a scud cloud or a small cloud coming through, and then as it got up here, it'd go faster and faster and sort of be sucked up there into the updraft. So those are the four things you want to look at. Well, once again, here's another view of that tornadic thunderstorm. What you'd see, the main storm tower is right here. You might have your mammatus up in the anvil, on the underside of the anvil. Flanking line towers, we've talked about all this so far. The heavy rain. The hail would be back here. Now there are different types of what we call, different types of clouds here. We call a tail cloud is the part that extends from the wall cloud back into the rain. And the way that forms actually is it's picking up this moisture and the inflows feeding in there, and you're getting condensation and a cloud's forming. So actually, if you see that tail, that's pointing towards that inflow. That's a sign that you have that inflow, if you see this here. Where it meets the base of the main storm tower, you have a collar cloud. Here's your wall cloud. Once again, a lowering of the base of the cloud, and this is your rain-free base. You'll have a lot of times you'll have the rain-free base, but not a wall cloud. Your tornado will always form out of the wall cloud, or at least usually. There's sometimes it might not, but almost always. And a lot of times out of the southwest or the rear part of that wall cloud. So that's where you want to look for the tornado to form. Here's another view of a supercell. Here's your wall cloud beginning to form. And what you have here, here's your heavy rain. So once again, if you're up here looking this way, you're not going to see much. What you're going to want is you're going to get behind it, usually to the west or to the south if it's moving to the northeast. And that's where you want to look for that tornado development. So another picture of the wall cloud. There's the tornado beginning to form. This might be the beginning of that tail cloud. It's hard to say. It almost looks more like little funnels. I don't think it is. This is actually the funnel. But this is pretty classic, where you have your rain-free base, your hail would be right in this area most likely, and then there's your tornado forming. Once again, you'd want to be down here spotting or out beyond, sort of beyond it into the screen. Or you could be here if it's moving off this direction too, but you don't want to be up here spotting for that tornado. Another picture looking underneath it, the wall cloud. Here's your rain. The storm's moving away from you here, or at least from left to right. This storm here seems to be moving from right to left. Here's your heavy rain moving this direction. There's your wall cloud. Good place to spot from back here. Now, if you're right back here looking towards the rain, that's not that good either, because you're not going to see, we're getting a little bit in that. The rain's out behind it. The wall cloud's going to sort of blend in with the rain, so that's not a real good spot either. You want to sort of look at it from a cross-section so you have light behind you, and that'll light it up a little bit. Well, there's the tornado. There's the wall cloud. This is a pretty obvious one. This gives you an idea, once again, of the wall cloud, what's going on. Well, you're getting the inflow. This is where that tail cloud would form. You're getting inflow into the storm. You're getting outflow. Remember, I mentioned before, the tornado will form at that interaction between the inflow and the outflow. That's where it'll form. and you get that spinning motion. Now what will eventually happen, I think I have a slide to show you, is this here, this outflow will gradually come around here and cut off the inflow. And that's what will stop the tornado eventually. But when you get something like this, this is formulated. Now, I'm really going to get a little complicated here. This is fairly new. This is actually very, very key to tornadoes. Now, let me see if I can explain this well. What you have is not just a spinning of the column, but you have a spinning of the air horizontally. Now, okay, let me go back. Not only do you have a spinning vertically, you have a horizontal spinning as it feeds in here. Sort of like if a person was standing here and throwing a football, a spiral, okay? And that football is going right along here. Well, if you can imagine this, as it interacts with this here, this outflow, it's going to push it up. So it's going to tilt it vertically, and that's what forms the tornado. Is this horizontal, we call it vorticity, horizontal vorticity, the spinning that's occurring down here, being pushed up vertically, gets faster and faster, then it forms up in the part of the thunderstorm there. Another tornado, more of a rope-like tornado, the dissipating stage. Some things that look like tornadoes, and we sure get them here in Iowa. There are a lot of different things. Just basically some low clouds. That's probably the number one thing. You might think that looks like a tornado. The main thing you want to do is know where you're at in relation to that thunderstorm so you're looking in the right place. That'll certainly get you started. But just a lot of low clouds. A lot of times we call these scud clouds coming in, rain-cool clouds. It's not a tornado. Look for the rotation of the wall cloud. Make sure you're in the right part of that thunderstorm. Sometimes you get here some rain, or actually this is probably clouds off in the distance. Once again, where's the wall cloud? Where's the rain area? You've got to look for the different components of that supercell. Here's another one. This is a little bit more complicated because you do have a main thunderstorm here, and here's your flanking line, here's your heavy rain. But once again, there's no wall cloud here, and if you were close, you wouldn't see the rotation. What you have here is just some extra rain, area of rain, a rain shaft, and that's not a tornado. There's no wall cloud there. What you'd want to do is you'd want to be sure, because perhaps there is a wall cloud, you're just too far away, but in this case, there is no wall cloud, there's no rotation, that's just a rain shaft. Once again, going back over everything here, here's your tornado, here's your outflow. What it's doing is, it's a little bit further around now. The reason it's clear air here, once again, I know I'm hitting you with a lot of different things quick. The reason it's clear air, or it's so bright, is because you're getting this downward motion. You're getting dry air brought down, and that's going to cut off this moist inflow feeding it. So once this works all the way down and wraps around, it'll cut it off, and then that tornado will dissipate. And that's what it's doing here. It's come all the way around. You still have the tornado. It'll stay there for a while. But look how far this inflow has to come. It has to bend around that. This is almost like a cold front. It has to bend around it, come all the way around and wrap around there. Eventually, it'll cut it all the way off. There's your tail cloud. Can't really see a real good color cloud here. Lowering wall cloud. There's your tornado. Wall cloud right here. Tail cloud, heavy rain up here. Rain-free base. Bright in here because you've got your mid-level winds coming down. By this time, it sort of looks like that dry air has come around, wrapped around, come all the way up here, and now your inflow probably has to come all the way around. So that tornado probably will dissipate fairly soon. This is probably moving towards the screen or into the screen. That's why sometimes it's hard to see because you're looking towards the rain in front of you. You want to look at it from the side rather than like this. And definitely you don't want to be in front of it because that's not safe for you either. Basically, there are three types of tornadoes. The small tornado, or mini tornado, the kind that touches down briefly. You have mid-sized tornadoes, and then you have the violent tornadoes, the real big tornadoes. They're very rare in Iowa. We occasionally will get them, usually in spring with an organized system. The ones that are common are the mini tornadoes. Okay, what to report? Well, usually what we would like to see reported is any tornado, of course, hail greater than 3/4 inch, or winds about 60 miles an hour or higher. if there is a wall cloud, we'd like to know, or a funnel cloud. A funnel cloud is just the out of the wall cloud, the tornado, but it's not touching the ground. Actually, if it's called a tornado, it's always in contact with the ground. Any heavy rain or flooding, we'd like to know as well. Basically, there are different procedures, and I'm not sure if the emergency management director's here. He can tell you after the program where to report, but certainly, you know, locally here you have your own procedures. A lot of times you can go through law enforcement, and they can get in contact with us as well. Okay, now we're going to shift a minute here to the video. I promise that I get you out on time, so we're right on time here. Okay, if I can carry this with me. Okay, can you get the button on here so I don't got so many wires going here? We're not going to get all the way through here. I'd like to show maybe about 5 or 10 minutes of video. And this will give you an idea of some of the things we just talked about. This is a supercell, and you can see with a little time lapse here the rotation in it. A little bit hard to see when you're just spotting, but actually if you run the rotation, you can see the whole thing's rotating. And actually, if you look closely, you can see not only is it rotating, upward motion. One of our forecasters got this music. I like this music. It sort of fits the thunderstorms here. Look how strong that upward motion is here. Once again, the ingredients for the tornado are the wind turning. That's why we're getting the rotation, because the winds are turning. If we had winds just from one direction, you might have an updraft, but you wouldn't have the rotation. The other thing we know, obviously, is that we have a very good amount of instability causing these towers. You can see this just every minute, so you can see how much turning there actually is. A lot of times, I saw a storm in Kansas, you actually saw real striations. It looks like a flying saucer sometimes if there's a lot of turning. Okay, this is looking off in the distance here. We have a fairly strong thunderstorm. I don't know, we can't tell a whole
kind of excited about
lot
this.
from it.
Yeah, we're both.
This is a real good storm chaser here. There are a lot of storm chasers right now. That's a big thing, especially down in Kansas and Oklahoma.
Yeah, that's starting to look suspicious there.
He describes it pretty good.
Which would put it this cell and probably that wall cloud. It's indicated by radar possible tornado, so it just might mean it's wrapping up.
There's your heavy rain.
And
You're going to be looking in this area, the rain-free area. No wall cloud right now, I don't believe.
Okay, you're county mapping there, and
No, it's not. Toto was an instrument that they try to set down in front of this. Right now, with Doppler radar, you can get a lot further away and measure it rather than trying to get right in front of it.
gonna zoom into the area here. Maybe put the camera on manual focus. It's looking pretty suspicious right in here. I'm looking for a possible tornado right
There's
here.
your beginning of the wall cloud right in there.
That's it. We're looking at a good wall cloud here.
Well,
At our back. Still didn't flow. Great rain-free base.
yeah,
I think we're seeing
nice wall cloud.
Once again, the heavy rain, inflow, the rain-free base.
Give you a view of what's going on. This is looking north now.
See where they're spotting? Where
There's the
they're not in the
sicko
rain,
Dave.
they're behind it.
Look at the sicko.
These guys have a lot of fun.
beautiful.
Yeah, it really is.
See a titch closer.
Yeah, I agree, but we've got roads to go, we've got options to go that way if we need to. I'm gonna zoom right in on this baby.
reported on running out of battery here. Straight west of us. There's nothing.
Very good wall cloud there.
Looks like it's flowing.
Oh,
See that inflow? I just noticed this here. That's your inflow going in there. See, it looks like it's probably moving up, accelerating vertically.
this is gorgeous. I'm going to kill the video camera here, though. We've got definite rotation there.
Yeah, I know, it is anticyclonic.
It's anticyclonic, but it's...
It'd be great if there were no other chasers and it was anticyclonic.
Yeah, that is anticyclonic rotation, no doubt. Boy, is that ever starting to look good, though.
We're looking at what we hope is anticyclonic rotation.
Boy, that is some serious stuff going on over there. That is...
That thing in the distance there,
Could that be a flanking line?
something, I don't know if it's to this guy. Boy, this airfield, we're getting south or something.
Yeah. Yeah, but look at that rotation.
It's now coming from the northeast.
All right.
Remember what we said before about persistence? It takes a while to form a
Look at
tornado
that
a lot of times.
rotation, though.
You can see the inflow as the little cloud particles are being pulled into it.
Look at that go.
You know, since we've had Doppler radar, it's amazing how many severe
I
thunderstorms
mean,
that
that is
have
the most
this,
intense rotation I've ever seen on
but don't necessarily produce a tornado. The rotating inside it is called a mesocyclone. The rotation inside the thunderstorm, the whole thing rotating.
That thing is huge. It's big, too. Let's pull over. Holy criminy, Mr. Tornado, April Lilliadol, I said I'd dedicate a tornado for you. I've got a monster wedge here. Monster wedge tornado. We're now, we're gonna be heading, oh my goodness, Bob. Bear with me now, it's a monster wedge, people. Monster wedge.
A
I've
wedge
never seen
tornado is
that
basically
big
a very
before.
big tornado. Spotters call that shaped like a wedge.
Bear with me, people. Monster wedge. Oh my goodness, Warren Bailey, eat your heart out. We've got a monster wedge here. Huge tornado. This is bigger than Wabasso. We are in perfect position for it. I'm shifting. Sorry, Bob. Oh my God. Look at that thing. Look at that tornado. I'm going to get out of the car here. Oh my goodness, it's huge! Ladies and gentlemen, time 4:55. Monster wedge tornado. It is huge. It is a big wedge tornado. This is a dangerous monster wedge tornado. Just absolutely monstrous. Strong inflow, probably inflow in the 40, 50, maybe even 60-mile range.
So to see the grass flowing in there, the inflows all into that tornado there.
Like this before. Incredible. It's starting to get behind the trees. What a monster! This is even better than Chandler.
I think we're definitely looking at a refreeze this car, man. That's our tornado.
The guy in here, I didn't realize it until I played this the first time. The person in here is a forecaster at our office. He was chasing in
Right
here.
ahead, there's definitely a lower base right there. Yeah, man, look, I can't tell if it's rotating. I can't get a sense of rotation.
So once again, what you're looking for, this would be sort of typical. The rain,
We're heading right off.
it's hard to say, but they're looking at this lowering here, inflow into it.
See some stuff off ahead of it. What's that? That almost looks like a wall cloud over there. Oh yeah. Doesn't it? That's the front. That's the front now. That's the front of the
See,
storm.
it's not real simple. They're a little confused now. You've got to sit there and look at what's going on. And
Look at this right here. Yep. This is lowering for time being. Here, why don't we stop right at this? Let's go over the hill. No, let's stop right at this thing right here. We can't see the bottom of the...
so that's probably the updraft there, because what it's doing, it's picking up that moisture and condensation as it's going in.
Oh my God, look at how fast that's moving in there, Fred.
That's Jim Bellis. He's one of our forecasters.
Ooh, I got that. Look at how it's moving into it. could be something, dude.
This could be a tornado. I'm not going any
going.
faster. It's my
We
God.
gotta top this hill. Sounds like we're gonna have an argument.
I know. I don't care.
Yes.
Right. This would be from the southeast. You can't really see the real heavy rain on here. Well, there, that's a little bit better if that's the same one.
What should we do? Do you want to just sit here
We're
and
in
ride it out?
Chamberlain.
Do you want to just ride it out?
We're gonna be right in the updraft, aren't we?
I want to get the hell out of here.
There's-
I'm sick of this. I can't take this. This is like... We got some DOT.
There's your heavy rain-free base. South Dakota. This would be the area you'd want to look at back
Let's look at
here.
like gustnados or something.
Aren't they? You're right.
A gustnado is along the leading edge, sometimes the gust front. Remember the part that's wrapping around the dry air? You can occasionally get a real small tornado that just spins up in
That's a
there.
tornado. That's just like we had before. That's a tornado. See it rotate?
Yeah, you're right. It is a tornado. You're right.
Holy shit, you're right. Holy shit, that's a tornado. Yep. You're right. Tornado. Oh, we're in a perfect viewpoint. Tornado right ahead there.
Actually, they're looking into the heavy rain a little bit. That's why the contrast isn't quite as good.
Right there. Still, yeah, or a gust front or
It's
something.
a gust front. We might have seen a gustnado. I don't know.
Look at that. Look at all the debris coming up.
That's exactly what it is. It's a gustnado. Look at it throw debris.
That's not a gust. Well,
That's... Is that a tornado?
I don't know. It's not rotating.
I think what I'm going to do here is go,
I think we
that's
better get about moving.
Got a couple things I want to show you real quick. You've probably heard of the new radar that we have out at our office, and I never like to oversell this radar because it's still not going to pick up the real small tornadoes. But on the other hand, it is pretty amazing what it can do. And the diagram here indicates, I think I'm going to take this out again, do a little walking around. This is, actually the radar has three different parts. You're going to be in a very good area here because you'll be covered very well by both the Des Moines radar and within a year or two, the Davenport radar, about halfway, I guess. It'll work very, very well. But basically, this is the radar part. It's hooked into a computer, and then the meteorologist looks at a workstation. It's totally automatic. It just rotates around every 5 minutes. It'll go up to 14 elevations and give us information. I got a picture of that here. This gives you an idea. We have clear air mode and also precipitation mode. But in precipitation mode, every 5 minutes, it would give 14 elevations and then come back down. And then the data that it obtains, we would look at. And I'd like to show you a couple of those, too. This is one from the Des Moines radar. And the date of this picture here is January 16th. This is a reflectivity. This is what you normally see on a TV radar. It's actually a radar, but that you'd see on TV. But look at the numbers here. It goes from a minus 28 return to a plus 28. Well, really, everything on here is clouds up until you get to about a plus 12 or actually more like a plus 16. So what we're seeing is these are all clouds. This is snow, just this purple in here. That's light to moderate snow. So what else can you see? Well, look at the streaking. Snow streaks. Well, with the old radar that we have, first of all, you just see one level, one color. All you know is you had some snow out there. You would have no idea, here you can tell the streaks, you can tell that it's much heavier here. You get a lot more information from this radar. And this is from a snow event we had not too long ago. Okay, well, we're talking about severe weather today. Since we haven't had a whole lot on our radar, this is one from St. Louis. We can call up other radars. So let's say we want to look at the Davenport radar. We could look at that once we get that. But this is out of St. Louis. And the reds here are your strongest thunderstorms. The intensity levels over here going from the blues to the greens to the yellows to the reds. So you can see where your heaviest storms are, strongest storms, as what some thunderstorms would look like. But anyway, that's sort of what we have right now. I mean, that's nothing all that new. It's quite a bit more powerful. But the reason we call it a Doppler radar gives us a map like this. Once again, every 5 minutes. This is a velocity, a radial velocity map. And what we're looking at here is the greens, or the negatives, are airflow towards the radar. The reds are airflow away from the radar. So what are we looking at here? Well, this once again gets a little complicated, but the radar is right here. Well, as that beam goes out away from the radar, when you get out, 50 miles or so, it's going to be higher up in the atmosphere. So you're looking at here right at the Earth's surface, but you might be 10,000 feet by the time the beam gets out here. So basically, the colors are going to be higher up in the atmosphere. So here we're looking at flow towards the radar and away. Greens are towards, reds are away. A north wind at the Earth's surface. Then you get up higher, towards and away. So what you're having is, we call this overrunning. You have a low-level northerly wind, an upper-level southwest wind, and that was a snowstorm. We had quite a bit of snow going on at the time. Gives us a lot of information we never had before. Here's another one that I thought was sort of interesting. This is, I don't remember, excuse me, how much snow we had down here. This was on February 25th. I know in Des Moines we had 4 inches of snow, and I think we had about 3 inches of snow down here. 6 inches, okay. 6 inches of snow, and it probably wasn't that well forecast either. But this was in the middle of the night, about midnight, and once again, greens are to flow towards the radar and reds are away, so we have a real strong northeast wind. This light green is the strongest, and it's real close to the Earth's surface, so it's showing the winds are very, very strong. But what's this out here? This is real interesting. Well, let's look at this again. Airflow towards the radar, airflow away from the radar. This is that convergence we were talking about. So we were talking about it in severe weather. You can also have it with snow. And this was a line, if we looked at the reflectivity at the same time, you'd see this would be a line of heavy snow right in here, right along where the winds are converging. Because they have to go somewhere if it's at a low level, and they're going to go up. So that gives us a lot of information we didn't have before. Something that I think is going to be very interesting that we haven't seen much yet on our radar, so I've got to get one from St. Louis again. This is something I think is going to be one of the most useful things from our new radar. It's a storm precipitation graphic. And we're usually on the scale here, either velocities, which is airflow or motion, or reflectivities, which is energy being bounced back. This one here is actually in rainfall in inches, so it goes from 0 to 15 inches. And you can see the yellows here are 9 inches of rain, and that verified real well. So, how do we do it now? Well, we might have an observer here, an observer here, an observer, here, and we might miss it if the rain doesn't fall in the rain gauge. This way, we'll have a good idea of where the heavy rain was. So if the observer was right here, we knew we got probably the heaviest rain. But if the observer's here, and let's say he's saying, 3 inches of rain, we know it's quite a bit more up here. So that's something I think is going to look, really going to help us with flooding type problems. So I have just a couple more here. This is, let's try it this way. There we go. This is at the same time, what we're looking at is a tornado showing on Doppler radar. And the tornado's with this thunderstorm right here. And you can't see it real good, but the radar is up this way. The greens are flow towards the radar, and the reds are flow away. So what we're having is a spinning motion here. You can see it a little bit better here at 2.4 degrees. Flow towards the radar, flow away from the radar. The whole thing's rotating. Actually, what this is here is your mesocyclone, the overall spinning of that thunderstorm inside it. Sort of like a cylinder inside there, a can turning. Whereas this is actually the tornado, which would be right in the middle. Actually, you're not seeing the tornado, you're just seeing the real close rotation. And let's see here. What else can we show from this one? One of the other things that we can show, this is that line, multicellular line that we talked about, reflectivity. Well, we can also look at the velocities now and see how strong it is. These reds here, how strong are those winds coming out of that thunderstorm? So we can look at the velocities for that as well. And finally, this here, we can do all sorts of interesting things with it. We can sort of slice a thunderstorm up sort of like a CAT scan. This is a cross section. We can see how high it is, 50,000 feet. We can see it's sort of bending here. You can sort of see the reds come here and then they go this way. It's sort of tilting. This is a reflectivity. Now, what do we see here? Well, first of all, this is a picture of a radar. The way the cell is out by itself is an indication that it could be a supercell, just the way it's sort of sitting out there by itself. The other thing that we see is, remember I was telling you about that real tight gradient before? Look how close these reds go to it goes from a blue to a red in a real short period of time. That's a good indication that you've got possible severe weather right in there. See up here, it takes a long time to get from that. This is actually a supercell, and this little, we call it the hook here, you have a tornado right there. Now what else is interesting? This is something that you might want to look at on TV radar. These little wings here. This is something I use a lot for severe weather. Sort of see how little wings here? This one has a little bit too. There's one here and one here. What that's showing is your upper level winds, at 10, 15,000 feet are coming in this direction, and this updraft here with all the rain is so strong that the winds have to go around either side. So we call this flow around an obstacle. Coming in here, can't go through it, so part of it's going around this way, part of it's going around this way. So if you ever see anything like that, that's telling you a real strong updraft, and that's a real good possibility of severe weather with that. So I promise we get through on time. I know we're running a little bit over. We've covered a lot of different things. I'll be around for some questions. Does anybody have any questions right now?
Can any of this be used to either predict or spot CAT?
No. Clear air turbulence.
Is there any new revelations on CAT?
No, not really, because really, we can see in clear air velocities, but what we're picking up is bugs and dust and things like that. So if it so happened that you'd have that, you could. But usually clear air turbulence is high in the atmosphere where there aren't going to be many bugs or dust, and that's why it's so hard to determine. I think with Doppler radar eventually we'll be able to maybe do something with it, but right now I have not heard that it can do much with it. Question?
What causes, when you in a thunderstorm, to go and see a water spout?
Well, some of the things with that would cause a water spout are somewhat similar to what causes a tornado, but it's much, much weaker. A lot of times water spouts, you don't want to go under one, but they've passed over boats and things, and sometimes it doesn't even capsize a boat, so it's much, much weaker. It does not have the structure that we talked about. Any other ones? Well, thank you all for coming out. Hopefully we won't have a real bad severe weather season, but I hope this teaches you a little bit of what to look for. Thank you for having me out.
Thank you, John. Appreciate it. Severe weather watchers, when you spot something, we'd like to have you report them to your base station or your net control, and have the net control then phone the local law enforcement center, and also phone the local highway patrol DOT station out north of town. So make 2 phone calls locally, and then another one should be made to John's office. Thank you very much for coming. If you have questions, please come up and talk to Mr. John Felton yourself. Oh, there are some handouts up here if you'd care to come up and pick up some handouts.